Where is it based on? 12. So divide the 11 by 12 to get a fraction of a foot that it is. So we're going to have to go, I can just do it, I'll just do 16 plus, not minus, plus, and then just do 11 twelfths. So it's going to be 16.916666 feet. So exactly, it's fairly straightforward. It's one of those things you forget how to do. And you could do it on small scales, like one of these, that 14.4, you know how many feet that is. It's 14.3333 repeating. Yes, right, exactly. It's a third of a foot. 4 inches is a third of a foot. Sorry, it's early to be making you guys do this. 15.9 is kind of the same thing. That's 3/4 of a foot, so 0.75. Everybody follow this logic? Okay, ish. It's okay. I don't know if that's slow. Yeah, I want to get the data in well because I want to make sure that we analyze it correctly. So 16.3 is going to be 16.25. 16.5 I can't do it in my head. Give me some change. 16.2. 17. Yeah. Some of these, because of the function of the number 12, some of these are going to be nicer, like 15.9 is 15.75. That's pretty easy. 17.6 is easy enough, 17.5. And so forth. But then you have 7, which is annoying. So I'm totally in agreement. I wish we would use the metric system for this stuff. Centimeters or meters or something like that. I was talking to an old friend of mine about the metric system. And I mentioned how we don't use it. We're one of the few countries that doesn't use it. He's like, yeah, but the metric system's dumb. I said, how's the metric system dumb? He said, it's a very convenient mathematical system, which I agree with. And he said, based on very inconvenient numbers. Or inconvenient lengths. I said, what does that mean, inconvenient lengths? He's like, well, think about what a meter is. Okay, I'm thinking about what a meter is. Because a meter is the basis of measurement of the metric system length. He's like, well, think about your height in meters. I'm like, well, I wouldn't think about my height in meters. I want to think about my height in something smaller, like 1/10 of a meter, which I think is called a decimeter. He's like, yeah, we don't do that. You don't do that in the English system. You think about it in feet. I'm like, yes, but comparing meters to feet is like comparing yards to decimeters. I mean, have you ever, who measures himself in yards? It's kind of dumb, right? I'm just about 2 yards tall. I'm just about 2 yards tall. Nobody says that. You kick out of bars for stuff like that. 15.03, 16 plus 4, 12. So I think there's a lot of 14.
So there's one more.
There is one more on L1. I had one more data set. Max got bored. I couldn't get 21 on the second one. I only got 20. He tired of this game. It's amazing what 6-year-olds can keep him focused for just about 12 minutes and then it's gone. So if I can't get it done in 12 minutes, then I'm off to something else. Let's go fishing. Okay. Ooh, butterfly. So, squirrels. Okay. So, we have a thought that the cantilever brakes are worse at stopping than the linear pull brakes. And I did try as best I could to control for every possible variable. Okay, every possible variable. I braked a few times with the new brakes to get the feel for them because I'd never felt them on my bike before. There was one that skidded, that 14.4 was a skid. I left it in. So what I did was I ran the track a few times with the new brakes, kind of got the pads worn in a little bit so they were worn in like the cantilevers were. But they skidded very, very easily. If you lock down on a V-brake, they'll close the wheels spinning. Physically, they make a lot more sense. Physics is actually kind of fun if you look at the actual pictures of the brakes. The way cantilevers work, if you look at that top brake, there's loss of force. So when you pull the brake lever, it pulls that wire up, which then pulls these up diagonally. Now, up diagonally, there's a loss of force right there. There's a loss of force. This is why, we've got some climbers in here, right? Got some rock climbers in here? Yes, rock climbers? Katie? You do everything, Katie. It's fantastic. You ever seen anybody climbing at Smith Rock? Have you ever seen them up there climbing through a rope that's clipped to one thing in the wall? If you do, leave. Because they're most likely going to get hurt eventually. They hook it to at least 2, if not 3 pieces. Why is that? Redundancy. In case one fails, you've got a backup. But also, there's a force argument to be had. If you run a rope through 2 pieces that are running off at angles, the force is split evenly amongst those 2 pieces.
So in other words, a downward force of, I'm 175 pounds. If I'm falling, if I fall off a climb and I'm lead climbing and I fall 10 feet, I generate more than 175 pounds of force because gravity's pulling me down. So let's just make it easy and call it 300 pounds of force. It goes up into those anchors and then is split 150 and 150, and then there's also a decrease because there's other places that force is absorbed too. So the same thing happens here. In a bad way, you lose the braking force on a cantilever brake. The V-brake, when you pull the lever, you see where the cable goes? That way. Not up, but across. That's exactly where you want it to go. Because across is where the pads go, across into the rims. So you don't lose any force at all. And that takes some getting used to. If you switch from cantilevers to V-brakes, I've seen a lot of people, they call it endoing, you've probably seen YouTube videos of that. You lock your front wheel, your ass wheel goes up, you go over the handlebars. I've seen many, many road bikers do that when they first ride a mountain bike. It's kind of cute. So as long as they don't get hurt, but it's not cute. But, so there's that's the mechanical advantage. So I ran it a few times on that sidewalk, or on that driveway to make sure I didn't skid the entire time. You don't want to skid. Skidding is the worst thing you can do for control on a bike, because then you have no idea where you're going to go. You essentially just kind of fishtail out, and then you can end up in the woods or in the river or wherever. So I practiced a bunch, but you did notice I did do one 14-foot 4-inch skid. I left it in. You guys can tell me what to do with it, if we should toss it, if we should keep it. Okay, we have a theory. The theory is they do better. Okay, I want a quantification now. I want to write this up in a journal. Right? This is the same thing you would do in any situation. You have a control group, which would be the cantilevers, and an experimental group, which is my linear pools. We got a theory that they're better. Let's quantify it. What should we do first, do you think, my friends?
What variable we testing?
Good. That's a fantastic question. I don't want to start the official hypothesis test yet, but Di asked a very good question. What variable are we testing? It's definitely mu, because it's feet traveled via braking. So this is cantilevers, canties versus V's. Yeah, I love that. So I mean, if you want to start a template, that's totally fine. We are definitely testing mu. So what exact average are we interested in testing? Well, I think, Di, you've asked the right question. We actually have more than one, don't we? We've got the cantilever stopping distances, and we've got the V-brake stopping distances, don't we? We've got two variables to test. If you will, we have a control group, and we have an experimental group. The control group is status quo, what the bike came with. Cantilever brakes, that just stock on the bike. I wanted to see if we could do one better by putting different brakes on there. We got two groups. Can I do the pair-off thing that we did with the commercials last time and the stopwatches last time? Can I do the pair-off thing where I look at one and the other and subtract them?
Yeah.
Why can't I do that? Why can't I do that? Give me one or two reasons.
One more.
Number one, I've got one more in the before than the after, so I can't pair them off because eventually I'll get down to one that doesn't link up. And also,
You don't know which one that's.
very good, Danielle. There's no logical connection between a data point in the before and a data point in the after, because there's no dependence between them. When you think about the experiments we did in class on Thursday of last week, we had a TV show and the commercial immediately following that show. There was a link. We had your thumb time and your finger time. There was a link, your brain controlling that. We didn't link Di's finger to anybody else's thumb, right? Does that make sense? Di's finger to Di's thumb, Shelby's finger to Shelby's thumb. There's a connection there. Is there any connection between a stopping time for a cantilever and a stopping for the V? No, not at all. These are independent. Independent. And since they're independent, you can't link them together, which means you have to treat them as two separate entities. This is going to be our first, if you will, control group experiment. This is our first data experiment where we actually have a control group. There isn't some starting and then change. It's a control group that is completely separate from the experimental group. You've heard of control groups. We've been talking about them for a few weeks. This is our first data set that actually has it. We have a status quo, the cantilever group. Danielle, what's on your mind?
Oh, no.
Oh, that was just trying to read my handwriting. Independent. Sorry. It was a pain. I apologize. So let's compare them. Let's compare them. What are some numbers we can pull from our data here? What do you think? They're averages. Go get them. Go get them, go get their averages. Hey, while you're in there, what else should we get?
Is there a shortcut to do that, or do you have to like?
Well,
add them all?
for yes, but I want to pull it out of the data. Danielle's got a question, is there a shortcut? Well, we'll give you one more stats, of course. Looking at 243. But there's a way to do the entire analysis at once, but I don't want to do that right now. I want to walk through the process first, and then we'll use the shortcut from then on in.
Okay, so just go and add more of them.
Oh God, use one of our stats.
Well, you won't, because, well, there's an extra.
No. Use one of our stats on L1, and then run it again on L2. You've got two data sets. Just do two different one bar stats calculations. Is that fair? I see what you guys are asking now. I'm sorry. So we're going to run the cantilever average and the cantilever standard deviation, and the V-brake average and the V-brake standard deviation. Yeah, we want to get two different measures for each of the data sets. I see what you guys are saying. Yeah. So I get about 23 feet for the canties. Plus or minus, oh here it is.
Why is it telling me to get this match?
Oh, you didn't do L1, L2, did you?
Well, I did not do
Oh no, just do, it's raw data. One bar stats for the first one bar stats for the other one. Yeah, there's no frequency counts. So just run, your data's in L2 and L3, is that what you said? So do one bar stats on L2, and then do one bar stats on L3. Do it separately though. Like this right here is one bar stats on L2.
Do you round up?
At this point, don't worry. If we need precision, we can use all precision we've got. This is more for understanding the process of what we're about to do. So I'm going to call that 23 just to go to 1 decimal, and then it's a standard deviation about 2.1 feet. Is that fair? Don't worry about rounding. Danielle's got a good question. Don't worry about rounding. Technically speaking, let's think about this. Who understands sig figs? You
It's been
do?
a long time.
If those measurements were what I've got, would it be 1 sig, 1 past the decimal would be all I'm entitled to?
Yes.
Is that right? I think so, yeah, I think, right? Because the
yours-
inches are whole.
yours is smaller.
Well, first of all, I would have run the experiment both with the same measuring stick. I wouldn't let Max decide which side went down. But, so it would be 1 past the decimal, I think, on that? Okay, good.
It's your lowest.
All good. So we'll just go with 1 for right now. Again, conversational, Danielle is okay. Don't worry about precision. We'll deal with precision in time once we have the shortcuts in place. And I'm going to run it again for the V-brakes. So 1 bar stats. I'm just going to change my list to L2. It looks like their average is about 16.4 feet. Hell yeah. Hell yeah. Plus or minus about 1.1. So based on just my sample, and this is, I gotta be careful with this now. Based just on my sample, I can make this claim. Actually, you make claims for me. Based just on the sample. Forget we're at 244 for a second. Pretend we're back to 243. So boring back then, I know. Okay, you probably liked it a lot more back then, didn't you? So make some claims based on just the sample. RV brakes better.
On average.
Yes.
Good, tell me how much better.
7 feet better.
Oh, I like that, 7 feet better. Or 7 feet less braking distance, huh?
Would you,
Dude, would you?
do you always have to say on average?
Well, I like what Danielle said. Don't yell at me, yell at her.
No.
Well, that's what we're doing now.
See, all I want you to do is ignore inference for a second and go strictly on these numbers right here. So Danielle says, look, 7 feet better. What if I then come back and say, yes, what if your original stopping distance was 252 feet? Does that mean with cantilevers it's going to be 243 feet?
Well, you have seen it.
Oh, good. Good counter to that. You could also go by it with a percentage argument. This is about, I'm going to make the numbers easy. This is about 8 feet less than this, yes? 8 feet is a third of that. So one claim you could make is brake a third faster. Brake a third faster with V-brakes. Take 1/3 off your stopping distance. That way you can counter my 250 foot argument and go, yeah, but you stop if it was 240 feet. You stop at 160. That's one argument. But Danielle also very cleverly mentioned the standard deviation. Do you notice something interesting about the standard deviations?
Almost double.
Yes! Cantilevers are twice as varied as the V's, which means my stopping distance for the V-brakes
More consistent.
are more consistent. Interesting. And again, I can't explain that. I can't explain the consistency. I wasn't expecting that. I was expecting lower stopping distances. I was hoping for lower stopping distances. I wasn't expecting it, I was hoping for it. Good, good. That's about all we can do. That's about all we can do with those statistics. What I can't do is, and this is why you're sitting in Math 244, other than just to torture you. What I can't do is I can't take this sample data and apply it to the whole population like that. Like, for example, the claim Danielle just made, which was fantastic for my sample, cannot be made in a population because it's based only on my sample. So what I need to do is I need to make it inferential, don't I? Yes, of course. I'm going to cut this down for a second. Come on, side point over here. What we need to do is we need a way, let's back this out a smidge. We need a way to slap this bad boy, over here, onto our null curve. Remember him? We need to slap our null curve over here, yes? If I stop this again.